So David Inouye comes to us from the machine learning department. There's actually a department of machine learning at CMU, having done his PhD at UT Austin in CS, and he went to Georgia Tech for undergrad. He's going to tell us, he's going to give us some more understanding of deep learning.
Thanks for having me here. Yeah, so I'll just kind of jump right in. Suppose a bank wants to automate lending decisions. And so a manager might say, deep learning, we've seen tremendous empirical success and a lot of applications. Like computer vision, natural language processing, speech recognition, self-driving cars. A lot of empirical successes here. And you might be asking, can we apply deep learning to lending decisions? So he asked his data scientist to go and see what happens. And initially, the data scientist might come back and say, well, deep learning isn't working. And then the manager, replies, have you tried, different hyperparameters? Have you tried more layers? Have you tried bigger layers? Have you tried a different training procedure? Did you read arXiv yesterday with this new thing that's come out? So there's, a lot of different things that you could choose. And maybe 2 weeks later, he comes back and it's like, 3 out of these 125 models that I tried, on GPUs and stuff, 3 of them work well, give good performance, And so this is kind of one thing, is that because of this lack of understanding, there's this kind of laborious trial and error process, which is fairly common still. So then, even after you do this, you might still want to ask things like, how will the model perform beyond kind of the original data set, the original training data set? A question would be like, we have these 3 models, they all have maybe similar performance, similar accuracy or something, and which should we deploy for these loan decisions? How do you make that kind of decision? And they might be very different, they're not necessarily similar, one's not necessarily like bigger or smaller than the other, or how would you make this decision? Or is there some way we can get at that? Another question you might have is, does the model obey some sort of business intuition, some kind of domain knowledge? For example, in approving loans, you might think, if you increase the loan amount, assuming all of the things are fixed, it should have a lower probability of being approved. It's a little bit more risky loan, so you might expect kind of a monotonically decreasing trend. This is, kind of based on business intuition and what happens in the real world and some understanding there. So you might think that, in the deep model might actually look like this, where it's, on the bottom right, where maybe it's not monotonic. So that could either be a problem with the data or the training procedure, or maybe it's just a bad idea to have a model like that out because it might, have some weird areas where it fails or something like that. Even if it could do well on the training data set, you might still want to be able to ask these questions. Another question, you might want to ask is, can the model be explained to users? Now, both to like domain experts or model developers and to lay users. For example, we deployed the model and, accidentally, approved hundreds of fraudulent loans. What do we do now? How do, we stop the system, okay, cool. But now what do we do? How do we kind of fix it? Because maybe we still think it can still be a useful product. How do we debug and fix this underlying model? So you might need some explanations for that. And then, there might be explained to lay users, how will these decisions be explained? Because often this can even be kind of a legal requirement that if you automate decisions like loan decisions or bail decisions or things like that, you need a way of being able to tell the applicant why they weren't approved. So, for example, you were not approved because of A, B, and C, you didn't have enough income or something like that. So if they're automated, we need automated ways of providing some sort of explanation. So kind of at a summary, this kind of lack of deep understanding of this deep learning kind of hinders practitioners and kind of users, because practitioners, there's this kind of very trial and error process instead of a kind of a systematic process that tends to be the way people go about deep learning right now. And also users, scientists, engineers, doctors, they're unable to validate the model, explain the model to lay users, and ultimately unlikely to trust or kind of adopt deep learning or complex models in general. So in this talk, I'll be talking about 2 kind of approaches to this lack of understanding. So one is kind of a bottom-up approach, and the idea is to use shallow learning, kind of like these small, simpler, wider boxes on the bottom, and use those to kind of build up a deep model. So kind of bottom up, take something we kind of understand better and use those directly as kind of components in a deeper model. And then the second way is kind of going down, top down, to explain the existing deep models. So we have some existing deep models that might work well empirically or seem to work well. And can we get at least a little bit of a lens into what's going on in these models to validate or understand these models? Again, you might not, just like any complex system, you might not be able to fully explain the model. But can we even get something more than accuracy? Accuracy is a single number and can be very misleading. So can we get at more of something of that deep model? So what is deep learning? This is just a little bit of a background slide. There's classical deep neural networks where you take, you essentially take the input, some d-dimensional vector x, you multiply it by a linear transformation, a matrix A1. Then you apply some sort of pointwise or nonlinearity to each dimension kind of independently. And then apply another linear transformation, multiply it by a matrix A2. And you continue this process. And so this is kind of the classic deep neural networks that have been around for a really long time, only become more recently rebranded as deep learning. But we might also think about deep linear functions. So people have usually thought that for deep learning, the nonlinearities is like the absolute key of why deep learning might be interesting. But you can even consider linear ones where you just have a matrix A1, multiply it by a vector x, and then just do another linear transformation A2. Usually people haven't done this because these linear transformations can be simplified into a single matrix B. So often they haven't done that, but there's actually been some recent work that even says that these linear, the kind of over-parameterized linear networks can actually help in optimization. So there's some interesting work there. But more generally, deep models, I would say, are these sequential transformations, essentially, or function composition, you might think. And if you kind of write them out, function composition looks like this, but if you kind of write it out like this, it's kind of layer by layer, you're doing a function transformation. You're transforming the input to a new output and then feeding that into another function transformation. So it doesn't necessarily have to have this kind of classic structure, but the idea is these sequential transformations, this function composition. And then, deep learning itself is basically estimating these transformations from data. So why use shallow learning kind of to build up these deep models? Like, why would this be? Right now, most deep learning models are kind of trained end to end. You kind of create the structure and then you run your algorithm and it slowly changes the parameters all at once. And the first thing is reuse here on the left. I would say we kind of want to take the algorithms, the insights, and the intuitions from this shallow learning that we have a much better understanding of and kind of lift these into the deep context. So we take some shallow components that are more like white boxes. We've studied them statistically. We've studied them from different areas. They're been empirically verified and useful in a lot of applications. And how can we kind of use those as components to build up a deep model? Again, in this case, we're not going to end up with a white, more complex model, or we might end up something with more like a gray model. There's still a complexity of the whole system together that we can't directly interpret or understand fully, even using this. But maybe at least we can understand each component better rather than training end to end. The second part is the modularity. So this idea is if we can we build up kind of a systematic way of doing this, then if we can improve one component, we move from the blue box to the red box, so say we make it faster or better sample complexity or a new algorithm or something like that, we can directly replace kind of a model we had before with kind of an improved component. And we don't have to change other parts. And they can also kind of be debugged and tested so you can focus on this particular simpler problem and try to improve that. So this is another background slide on kind of what are classical shallow models. They're generally these scalar functions, basically, that take a d-dimensional vector and output a scalar value of some sort. So some examples are like density estimation, like Gaussian density estimation. You take an input and then you get a density value. Or like regression. In this case, this is just linear regression. Or classification. These are the classic, like a decision tree. These are classic shallow models. This talk, I'll be talking primarily about density estimation, kind of using shallow density estimation to build deep density models. We've done some initial work on the regression classification, but still kind of working those details out. So here are a few example shallow densities. These are kind of the components, building blocks that we'll be using. One is kind of an independent density on the top left here. This is like 2 beta distributions. So obviously an independent density is fairly simple. Then we have like a multivariate Gaussian density is another example of kind of a shallow density, or a Gaussian mixture model. And then on the bottom right, we have what we call a decision tree density, where basically each rectangular region has like a constant density value. A little bit less well-known density estimators, but they can be useful. And in this case, we're in the density estimation kind of unsupervised learning context. So the colors are just to kind of show you different regions of the density, but we're not doing classification. We're doing density estimation. So how can shallow learning be used to construct deep models? So naively, even just because we know kind of the signature of these shallow models, we go from a d-dimensional vector to a scalar. Now you can't directly compose these, right? So our deep models are these compositions of functions. And so you can't kind of use them directly as deep components. So we must map the model to a transformation. Essentially this mapping omega that will take as input the density, which is a function from D to R. And we map that to now a transformation that goes from a d-dimensional vector to another d-dimensional vector. And so now we could actually then think about composing these. So that's just kind of the interface, why we need a mapping omega. It's just, you can see from the interface. So then what is kind of the appropriate kind of mapping? What's a reasonable mapping to map a density? So we suggest there's 2 things, at least, that this mapping should have. One is that we would like it to encode the density. So we want basically all the information about the density to be somehow encoded in this transformation. And roughly what that would mean is that kind of there exists an inverse mapping. So we can take the D, which we'll call a destructor, which we'll see why for the second property, and be able to kind of recover the original density. So we want to kind of encode everything, all of the structure in the density into the transformation. And so then the next part is to ensure that this D destroys all the patterns in the density. So when you apply it to the random variable. So it becomes a maximum entropy distribution. So let's look at an example. So in the univariate case, the thing that the CDF transformation is kind of this mapped function. So if you take, for example, a sample from this distribution over here, some sort of multimodal distribution, and then you apply the CDF transform, you get the uniform distribution. So that's kind of the maximum entropy distribution. So that's part of the property 2. But similarly, you can kind of go backwards and sample from the uniform distribution, pass it through the inverse CDF transform, and you get a sample from the original distribution. This is like inverse transform sampling. This is great for univariate case. So then we kind of basically generalize this for the multivariate case. So we call a density destructor is kind of an invertible transformation, such that if x is a random variable distributed as p of x, then we have this d of x. When you apply it to that random variable, then its new distribution is a uniform with the same dimensionality. So it's kind of a generalization of this univariate CDF transformation. And here we have, that's this inverse mapping. So we can take our destructor D and get the density, which is basically just the determinate Jacobian. The Jacobian is essentially multivariate generalization of the gradient, basically, when you have a vector-to-vector function. So this gives us the density in closed form. So this is one really nice property of these types of probabilistic models, is that they have this closed form density. Some things like graphical models don't have a closed form density. I'd like to know that this is different than the multivariate CDF function. So the multivariate CDF function takes a d-dimensional vector and outputs a number between 0 and 1. So this is not it doesn't output a d-dimensional vector. So the transformation and the function, I kind of use those terms separately here. So there's like a transformation basically, and there's a function. And it happens to overlap in the case of the univariate case, that the function and the transformation are the same. But it's not true in general for like generalizing to the multivariate case. So this is some of the examples of kind of what this for a single shallow density. So the kinds of transformations that will happen if we apply these destructors. So like this is the independent. So this is why the color is kind of helpful. You can kind of see which regions, this is the original density, and then after you apply the destructor, it becomes uniform, essentially. And so you see different ways, and like for the decision tree density, you're kind of, in some senses, resizing these rectangles so that the resulting density is uniform. So if the original true density is just a shallow model, then you could just do this in one step. But if it's not, if the density is like more complicated than one of these shallow models, then we'll this is our kind of find and destroy deep density learning. And so the basic process is kind of a find and destroy process. So first you kind of find some patterns or some structure in the data using a shallow density estimation, P1. And then you use your map to take it to this transformation D1. And now you pass the data through that transformation. It kind of removes the information you found. So it's kind of like taking one piece off of a Lego. You're given kind of a Lego set that's already made, and you're taking one piece off at a time and kind of recording how you do it. So then you will learn another density model using shallow learning, and again map that to another transformation. And you keep repeating this. So each time you're kind of removing patterns until you get closer and closer to the uniform distribution. So yeah, this is kind of, again, we're going from data, and as we add more and more layers, we get closer and closer to the uniform distribution. And if we want to compute the density, now it's just kind of a multiplication of these Jacobians. So that's how we can kind of get a closed form density estimate. And then kind of in the opposite direction, because these were invertible transformations by construction and by the way that we set it up, then you can go from a uniform and go through the inverse transformation and essentially get samples from the data distribution. So this type of probabilistic model, you're able to get closed form density and kind of like exact sampling, which is real nice. So let's look at a little bit of an illustration. On the top left, we kind of have the original training data without any transformation. And as we add more and more of these destructors, so we estimate a density and we apply then the corresponding destructor, we slowly move the training data basically towards the uniform distribution here. So with a lot of layers, it gets closer and closer to this uniform distribution. And then kind of on the flip side, this is the implicit density. So this is in some ways kind of going in the opposite direction. There's kind of, as you destroy stuff, the reverse process is like putting it back together. It's like you recorded all the steps of taking each piece off of the Lego model, and now you're kind of reversing it and saying, okay, now give me all the pieces and I'll put it back together. So it's kind of like we learn the density kind of implicitly by removing stuff. So this is kind of the implicit density at each layer. If you look at just at layer 2, and you've only had like one or two destructors, in this case we use some of those tree densities that were based on these rectangles. So that's why you see some kind of artifacts of the rectangles in layer 2. But then as you add more and more layers, you start seeing these concentric circles, which is like the original density, closer to the original density. So this is some results on kind of this idea of regularization. So in shallow learning, we have a much better idea of how to do regularization, like cross-validation and tuning hyperparameters. There's been a lot more study on this. For deep learning, it's like there's a lot of techniques, things you can do. It's unclear. We know we're doing something, but it's a little bit harder to know what's the right thing to do. Whereas like for an SVM, there's kind of a standard thing to do for SVM. We know how to do that. And similar for density estimation, shallow density estimation, we often know different ways to regularize. So this is kind of showing that we can take some of those insights, the way that we understand how to do shallow learning regularization, and kind of do deep learning regularization. So on the left, we have kind of just the shallow models, which is just a single layer in some ways. And then we essentially build up, we keep adding destructors until it starts overfitting the data, the test data, right? So we greedily add more and more layers until it starts overfitting. And in the parentheses, we have different regularization parameters, and we can increase the regularization essentially of each shallow estimator, right? And so as we increase the regularization here, we're able to kind of go deeper because each layer is doing less work, kind of. But we're also able to get better performance. This is the likelihood. And this is shown throughout different ways of different types of these deep models. So the main thing here is just that, again, we're trying, you could even though in this case we fixed the regularization parameter and then just added more layers, you could think about actually using cross-validation on each layer to find the hyperparameter. For each layer. So you can it could kind of auto-tune itself based on stuff we know from shallow learning, how to do shallow learning regularization.
So just to clarify,
yeah.
The knobs are the regularization parameters per layer versus the number of layers. Do you guys have theory on how to trade off between those two?
That's a great question. Not yet, no. This is just empirical to show that, it seems to be that these trade off. But yeah, those are in some ways two different types of regularization. One's kind of the depth and one's the per layer regularization. It's a great question. So this is, that was just on a smaller data set, a toy data set, and this is kind of on a higher dimensional data set. MNIST and CIFAR10, these are two image baselines. We're not using them because they're images in this case, just because they have interesting dependency structures. So we're kind of agnostic to the fact that they are in the domain of images in this case, just using them as illustrations. So on the top, we have a lot of these baseline models that are kind of classically more like the deep learning, deep neural network-based models. And then we have our model down here, which essentially just uses a PCA algorithm and a histogram estimation algorithm. So two very, very well-known shallow kind of learning models and learning algorithms. We've studied PCA like crazy. We've studied histograms, univariate histograms like crazy. So what's interesting is that just using these two very simple components, we're able to get some good likelihood in comparison to kind of some of the baseline models before. And then we're competitive on the CIFAR10, not as good as the top model here. But mainly the real point here is just to say we're using some really old methods. I like old methods sometimes, I don't want to throw away all of what we've learned in the past for what is new. And so I think this is one interesting example of being able to use stuff we really know about and kind of extend it a little bit, but not throw it all away, which is what I think some deep learning, it kind of throws all of what we've learned before away. So this is a small sample experiment where the number of dimensions is 63 and the number of samples is 30. So the number of dimensions is higher than the number of samples. And the key here is we're trying to show that we can use, so the statistics community, again, has developed probabilistic models to specifically handle this high dimensional or small sample setting. And so we're trying to say, okay, we can replace components like PCA or something like that with more advanced versions in some ways of PCA and Gaussian estimation. So at the top, we just have these independent density estimation. Here, these two models here are basically the statistical models that have developed in that community that are specifically designed for these high dimensional settings. And so then our models basically just take those models and are able to make, add layers to them. So compose them in some ways. And so that's how we're able to kind of lift these, very carefully designed statistical learning models to kind of this deep context and get some improvement. And if we look at kind of like the baseline mainstream deep density learning, they kind of struggle with this very small sample setting. So this is kind of an example of trying, that we can replace these components. If we say this layer always does PCA, but we want to use different types of PCA maybe, then we can replace it with a new PCA. So the future vision for this destructive learning, I'd be interested really in trying to develop this kind of destructive learning subfield, kind of a different approach of thinking about this kind of find and destroy thing by creating these deep models. So you find some patterns using some shallow learning, and then you remove them, and then you remove them through a transformation of the data. So then you have a new data, and again find something and remove. This basic approach. So I want to go beyond, density estimation, thinking about how can we use classification models, regression models to be able to do this, as well as any other kind of. I'm really interested in any of the shallow learning, even in like time series data or things like that. It would be interesting to see, like, okay, what kind of structure is it finding, and then can we figure out a transformation that kind of removes that structure, and then do it again, and so forth. And then going beyond invertible destructors. So there's things like, autoencoders tend to compress to a very small dimension, and it's kind of this assumption of some manifold, some low dimensional manifold. So how do we think about, right now we've used only invertible destructors, but how could you, what does it even mean in the density estimation context to think about non-invertible destructors, that have different support than the original data or whatever. So trying to think about how can we still use, is there like kind of like pseudo inverses in some ways for this type of thing. And then discrete destructors. So some of my previous work has been on modeling count value data, and discrete is often harder in certain kinds of ways. And so you can't have, for example, a deterministic destructor. You can't take a Bernoulli random variable and convert it to like an unbiased Bernoulli random variable without some sort of probabilistic transformation of the data. There's no like deterministic transformation. So that would be, thinking about what is the minimal probabilistic transformation maybe that moves it. And then I'd be interested in applying some of this destructive deep learning to what I would call middle ground applications. I think might be the sweet spot for this type of thing, where you want more power than kind of the shallow learning, but you don't want the full-fledged deep learning to be applied, because you might want a little bit more interpretation, or maybe you have a shallow learning model that works pretty well, but you want to just try to see if you can improve the performance a little bit. So this might be a way to start with this shallow learning model and just add like one layer or two layers instead of like starting from scratch with a deep learning model. And then thinking about maybe some, people are really interested in image type density estimation and things like that. So can we, think about image specific destructors? So I've talked about this kind of bottom-up idea, and so now I'll start talking a little bit about this kind of top-down explanation idea. So why model explanations? The main thing is because I think accuracy is insufficient for many applications, or any other single metric. For loan approval, you might ask, could the model make a catastrophic mistake? You don't want to deploy a model that might accidentally approve $1 million fraudulent loan. Like, you want to kind of be assured that won't happen, or something like this. Or, for bail decisions, is the model biased because of some sort of historical discrimination in the data? So all the data is biased, and so you don't want to build your model just directly based on the data because it's biased, and kind of perpetuate these problems. Or you might think about, does the model agree with some sort of doctor's knowledge? When they see this, they're like, oh, that makes sense, or no, that's kind of contrary to what we actually know is true. So previous local explanation methods can be difficult to interpret. So one of the most common ones is called this local interpretable model agnostic explanations, or LIME. Probably one of the most popular now in the machine learning community, at least. And so the idea in that work is to kind of approximate the model in some kind of local neighborhood. So you have a target point, you're interested in like a particular person. You're saying, this particular person applied for a loan, let me give an explanation for that person, or this particular image, or something like that. And you want to approximate the model, some simple model around that point. And that model should somehow be inherently interpretable, which is a little bit, people question what inherently interpretable means, but let's suppose that you agree that sparse linear models or trees are inherently interpretable. So then you might get a model like this, right? You get a line that passes through this target point or something, and you say, okay, that's the approximation of the model around that point. But part of the problem is like we don't know, the approximation error is unknown. Like how close is this to the real model? I mean, it's a model. It's probably better than random, but how close is this to the real model? And like, where is the model valid? Is it only valid kind of like in a very small amount around this, or is it kind of valid really far away? Or it's hard to tell these things. So maybe the real model is like this. Suppose it's just a single dimensional model, and it's unclear. Was that model good? I mean, it's definitely like better than nothing, but how do you really interpret it directly? So our take is kind of that counterfactuals are a natural way to explain. And so the main idea here is like given a factual point, some target point, x0, what would the model predict if we change one or several features? So kind of directly what would the model do differently if we change this in some way? So some examples that you might think about is like, why was I denied the loan and your income was too low? If instead your income was 60,000, you actually only make 40,000. But if you did make, in a counterfactual world, 60,000, the model would have approved your loan. Or is the model biased? If you change the race feature, does the model predict differently or something like this? Answering these kind of counterfactual questions with respect to the model. And so we're going from, we want to go kind of from these point-wise counterfactuals to like a single counterfactual statement or question and answer to kind of answering a lot along a single like univariate curve. So let me give an example of these. So here we have explanations for two loan applications. And essentially, we hold all the other features fixed, and we only vary this one feature. And these features were selected, as I'll get to later. These were specifically selected for this loan application. But in this, for example, the original prediction is like these dotted lines. So we're trying to find maybe the features that differ most if you had switched this feature in some ways. One nice thing is these are exact. So there's no approximation in the sense of these solid lines are in fact the true model's prediction. Like we didn't approximate the model and then do something with it. Like these is actually what the model would predict if you changed this feature. And then also it's non-local, or it can be non-local in the sense of you can, for example, in this bottom plot, the original duration of this loan application was 25 months, but you can see, far away what would the model predict, far out at like 58 months. So it's not just like really local around that particular point. You could think of going kind of far away from the actual point. And then these explanations, we hope, can show kind of both the unexpected and the expected. So the unexpected, for example, in this plot, you might see that, it might be interesting to think that having a small checking account is somehow worse than having no checking. So this might be kind of a model problem. If it'd be better for this loan application to have no checking, which seems counterintuitive. So this might be some sort of bias in the data of why there's a higher probability for a no checking account. But then you also might be able to validate kind of things that you might expect in the data. So as a domain expert, you might expect certain things to be true. So for example, again, we talked about this monotonicity. So as the duration increases, you would expect the probability of approval to go down. Now this is holding all the other features fixed. So if you just change the duration, you would say that longer loans are more risky, and so it makes sense that the probability of approval would kind of monotonically decrease in this situation. So I think both of these things are useful, showing what's unexpected as well as possibly validating what you might expect and giving you some reason. So this is a little bit more formal idea of what we're talking about here. So first we have this kind of curve. this phi of x0, and it takes a value between 0 and 1, and outputs something in the input space. So it's a univariate curve in the input space. And then this is kind of the counterfactual condition, is that we want some point along that curve basically to pass through the original target point. So this kind of anchors the interpretation, saying like, okay, well, we know this is what it originally predicted, but we can see how it changes differently along this curve. And then the curve explanation is fairly simple. It's just the curve and the function values, the exact output values along that curve. So we actually use the real model f. This is, again, we're not using any approximations. It's kind of like what you see is what you get. That's actually the function output. Of course, we're only showing a portion of the model, right? So there's definitely an incompleteness here. But at least we show the exact output along the curve is the idea. And then there might be many possible curves. So that's why we want to optimize some sort of utility of curves to show. We can't show them tons of curve. We only can show them probably a small amount, or maybe even just one curve to show them. And we want this curve to somehow be semantically simple so that there's some way they can interpret the curve. And if you change like 20 dimensions at the same time, you say, well, if you change your income and you change this and you change this and you change this and you change this, like it starts becoming not interpretable. So you want it to only be changing several dimensions usually to really be able to understand these explanations. So which curves are interesting? We kind of approach it from this philosophical conception of knowledge as justified true belief. And the idea is we want to increase the user's knowledge. And knowledge in this definition from philosophy is that the proposition has to be true, the subject has to believe the proposition, and the subject is somehow justified in believing the proposition. And so how this goes with explanations is like the proposition is kind of a counterfactual question and answer, for example. What would happen if I change this? And what's the answer? What would the model predict if I change something? And the subject, of course, is like the user of the explanation. And so, how well does the model, does this curve kind of move the user's explanation towards more knowledge about the model? So this is not necessarily knowledge about the real world, but it's knowledge about the model, their understanding of what the model does in its internals. So it could be the model is doing something bad, but at least they would know it's doing something bad, right? That's kind of the idea. So there's kind of, again, two aspects to this. One is correcting false beliefs. So they might believe that the model is somehow monotonic, but then you show them an explanation where it's not monotonic, and then it corrects their belief that they think, that it's some sort of monotonicity or something. So that's like correcting, but also you might want to justify. So they might believe it's something that's true about the model, but you then, when you show them an explanation, you kind of give them then some justification for their belief. So that's kind of like validating something. And that kind of also increases their knowledge about the model. So we gave at least two utility functions. One is kind of a model comparison utility. And so this idea is like kind of encoding people's prior beliefs as kind of another model. So maybe this is a much simpler model. For example, maybe you elicit some sort of linear model from experts and say, okay, this might be your prior belief about how things should interact. Now let's see how it differs along this curve from the model that we've fitted, the F. So this kind of finds the biggest deviance from that. The other one is obviously this constant model, which is just like the original prediction. So in the previous ones, I'd show that the dotted line was just like the original prediction of the model, which features are like kind of most impactful in changing the original prediction. And then this other one is this, I think in some ways more interesting, is this monotonic utility. So this is measuring the kind of non-monotonicity. So maybe a prior belief, again, in like the loan applications, is that every feature is kind of monotonic. You'd expect that, if you can increase your number of bankruptcies, well, your probability to approve it should go down, like every time. Or if you have less money in your checking account, you should be less and less likely to, maybe it's flat or something, but you shouldn't increase the probability for certain, So that might be an assumption, a prior belief kind of model, an expectation about the model. And so this is kind of the positive derivative. This is kind of the absolute value of the negative derivative, just to kind of explain this function. So if it is like always, if it's monotonic, one of these will be 0, so the minimum will be 0. On the other hand, if it goes up and down, then both of these will be positive, and so the utility will kind of go up. So it's measuring kind of the non-monotonicity of the curve. So yeah, again, going back to that example of believing that something should be monotonic with respect to, for example, amount here. This we optimize over like all possible features, and we show the direction for this loan application 1 that is the least monotonic in many ways. So you can see here there's like something weird happening in the beginning, which is why the monotonic utility is higher than 0. So we have two loan applications. At the top we have a random forest, at the bottom we have a kernel SVM. And both of these models actually have like nearly identical accuracies. And so if you want to select a model based on, you can't select it based merely on accuracies, but seeing these explanations and having this common, prior belief that things should be monotonic, then you might want to suggest this kernel SVM is kind of a better model to actually deploy. Because it's mostly monotonic. Like there's just one dimension that's like barely not monotonic, but mostly all other dimensions are monotonic. Whereas in this random forest model, there's some non-monotonicity. So it might be able to help you in selecting a good model to actually deploy. And if you kind of optimize over multiple features, so for example, if we optimize over 2 features, we find that duration and amount, and used kind of in combination, you actually get even almost a sinusoidal non-monotonicity. So you can find this even maybe more surprising, unexpected behavior if you optimize over more than just a single feature. And then we're also thinking about out-of-sample behavior is something that people care a lot about. Again, in like loan applications, we have a training data set, but can we always assume that the new thing that we have is going to be like our training data set? Well, oftentimes in the real world, no. There's distribution shift, or maybe like you only approved loans that were $5,000 or more, but you want to try to approve loans that are now $3,000, right? You don't have any data on that because you've only approved $5,000 ones before. So like how you want to kind of see, is it doing something reasonable outside of the domain we might already know about? So in this case, we're just using these stop signs as a way of illustrating this out-of-sample behavior. So you might see as you kind of change the brightness here, there's kind of a breakdown point where it stops predicting the stop sign well. And that might seem reasonable for these ones that are really white, but then there's somewhere it's like if it's a really bright day, does it mean that this model would fail? If it's a really bright day, it might break down too early. So being able to see, even though these images weren't in the training data set, kind of how does the model do on the outside? Similarly, we see on this like rotation, you actually see this non-monotonicity here, where it gets bad when the stop sign's vertical, but then somehow gets better again when the stop sign's flipped over. So at least sees that maybe it's looking for something white and horizontal, but not actually reading stop. And then here we have, if you desaturate the image, if you remove the color, the probability of stop sign doesn't really decrease. It just stays almost constant. This could be, depending on how you're wanting to design the system, this could be good or bad, right? To humans, red is very important to identifying stop signs. But maybe it's kind of robust to that. That could be a good thing for stop signs in general. But yeah, it kind of depends. But it kind of gives you some sense of the out-of-sample behavior. So if you desaturate the image or something, what would it look like? So kind of going along this direction, I'm interested in doing density explanations. So applying this to how can we explain density estimation models? Because that's my strongest background is in kind of this density estimation that I talked about kind of in the first part. And these are unsupervised methods, and so being able to really get a lens into those, most people have just looked at parameters of density models, like a Gaussian graphical model. They look at the correlation to the covariance matrix. They try to interpret that. But can we do something more general, especially for these deep densities that don't have a direct parameter-wise interpretation? More generally, kind of this process of prior beliefs and expectations, I think this is kind of critical in defining both in evaluating explanations and thinking about explanations is what do people expect, what do people want to see, what do they believe the model should do, and being able to formalize those really. Formalizing those as well as kind of understanding what they're interested in, what their prior beliefs are. I think this could lend itself to kind of these personalized or kind of dynamic explanations. So if you had a model for what someone believed kind of about the model, you could show them things that were different than what they currently believe. And then as they're like, oh, okay, that makes sense now, you kind of add that to their prior beliefs and show them something different. So I think this would be a really interesting dynamic explanation. And more generally, I think this idea of kind of assert type statements, like error checking, building up kind of a system for saying, if you want to check these types of properties, like monotonicity, for example, then you could kind of add these to your model development and try to be a little bit more precise about what you're interested in a model. As well, coming off of this, there's a lot of question about how to evaluate explanations. So this is like kind of a new area in machine learning is these explanations. And I kind of want to take that tack of thinking of how does it increase your knowledge again. And so trying to kind of formalize what does that mean in other contexts and different types of explanations, how do they increase someone's knowledge? Again, that really hinges on being able to think about prior beliefs and things like that. How do you formalize those concepts? So I think, do we want time for questions? Or should I go further?
Questions? Fine.
So when you put together these shallow models and like constructing a deep model from them, how are they connected? So are there weights between them, or is it just straight up function composition, or like how do you connect?
Right. So yeah, it's just basically just straight up function composition because the mapping, that omega, that maps like a density to a d, that d is already kind of just a normal transformation, so you could just directly compose these. So that mapping is the key part, is how do you create that mapping. And in certain cases, like an independent density, for example, is just like an independent CDF on every dimension, right? So that's like a simple case. But then for other cases, like, for example, the tree density, there's like a way to design that mapping so you have a different, it's not always obvious. There's not like a canonical way to do it all the time. But once you have that mapping, you're just directly mapping the parameters of your density model to a transformation. And then however you do that transformation, there's no constraint on how you design that destructor as long as you know it's invertible and things like that.
Dirk and then Rebecca.
So in the latter part, how do you determine when somebody's prior constraint, so monotonicity of lung, is not in fact justified? So for example, in sentencing machine models, there was certainly lots of racist decisions, decades ago, that people might go like, oh, this doesn't match my intuition of the data, but their intuition is wrong. So how do you indicate the fact that their prior model is flawed, as opposed to, take it for the monotonicity example.
Right.
How do you basically get what is their prior belief and indicate that is flawed in a structured and justified way in that example?
Right. I think that's a much harder problem than just identifying that one exists, maybe. Right. So yeah, I think that's more. There's a confounding factor there, right? That I think in some senses requires more tools, right? So you see that it's not monotonic. So then you have to decide, I think that question about which one's right is actually almost more of a philosophical question, or more of like we need to go deeper into why did it happen that way or something like that. So I think there's not an obvious way, right, to say, you show them something that's non-monotonic. Okay, it's different than their beliefs, but again, we're showing them, an explanation with respect to the model. Right. So then they have to decide, was my model wrong, or was, like, is the model wrong, or is my some prior beliefs need to be reframed, right? So I think you kind of need like a whole nother set of tools to say, all right, I see there's some sort of problem, and am I just going to be like, no, there's no way that can be true, or like, is there something actually interesting either in the data or in the like,
Or missing parameters.
right, or like the real world phenomena maybe is like that, right? So that would be, again, I think that is like a whole nother kind of interesting question, is like, how do you decide whether it's the model that's wrong, your prior beliefs that are wrong, or something like that, yeah.
Yeah, when you're transforming the density to the multivariate uniform,
Mm-hmm.
then you must be comparing, how similar your transform is to the uniform. So I'm curious how you do that comparison, like what you're minimizing there.
Yeah, you can show that you're either equivalently increasing the entropy at each step. So, or you can show that you're kind of the KL divergence. It's equivalent to say the KL divergence between that distribution and the uniform distribution. It just is decreasing at each step. So yeah, that's what you're optimizing. And in some ways, it connects to maximum likelihood. So if you're doing maximum likelihood at each step, roughly like that difference between using an identity transformation and using the transformation you end up using is essentially the added benefit you get at each step.
Yeah. Which of your papers covers the second half of the talk?
Oh, it's actually a paper under submission right now. Yeah. Thanks for.
It's not on archive.
It's not an archive yet. Yeah. It's a good question.
Yeah.
How will you scale? I mean, which one do you think scales better in terms of explaining large networks?
You mean which part of the talk, or which?
Not which part of the talk is it? Which one among the two ones with the shallow models versus the explanations, large explanations? I mean, have you tried applying it to? I think you went so far as to say 50 layers plus stuff. So, have you tried applying the same kind of decomposition into shallow models for larger networks, or for larger, or for models which use a huge number of layers?
So you're saying, do you use the explanation for larger models?
One how are the shallow one? I mean, do these two converge? Have you applied both of them to the same kind of model and you find that they converge?
The two different approaches, you mean? No, in some ways these are kind of, separate in the sense of like, you could obviously apply the explanation to the shallow learning side, but they're not like, maybe there's an interesting thing to try to connect them more carefully, but they're not like tied together. It's not like we've done something that has used both of them at the same time, for example. It's kind of.
How do you take like whatever network you're trying to explain, say some network N, and then you try doing this to get an understanding, and then you try doing this independently and then see which one approximates your actual network better. In that sense.
Not quite sure.
Like the first technique is not a technique of interpretation, it's a way of building a deep model, right?
Right. Are you saying, is this deep learning model like more easier to interpret in some ways from?
Or once you actually build your model, I mean, because I mean, you're trying to get an understanding of how the entire network operates. I just wondering which one you prefer. If you got a new network that you have to analyze, and which one you go on, or which model you adopt.
So
I see.
this first part of the talk does not provide an explanation of some arbitrary neural network. It provides an explanation of the network that he builds.
Right. Yeah. So yeah, you can't. That's actually an interesting direction, which is doing kind of going the opposite.
And interpret it using that.
Right. Like try to go backwards and see how does the deep model, what are the shallow models within the deep model, or something like that. Kind of reverse. In this case, we're taking shallow learning and we're doing it for deep models. The other way is to kind of go deep models and try to figure out which shallow learning models they are. So it's kind of.
But I thought essentially you were trying different trial and error and try to build up an arbitrary network.
Right. So that's like the model building part. Yeah.
So I'm glad there was a lot of interest. Let's take the rest of the questions to the reception and
Okay.
thank the speaker.
All right, thanks.